According to Stigler's law of eponymity, no scientific discovery is named after its original discoverer. Notable examples include the Venn diagram and the Pythagorean theorem. What about discoveries that are thought to be named after their discoverer, but actually aren't? A good example of this is Euler's number, also known as E. While Euler did name it E, he didn't necessarily name it after himself, so he didn't intend for this coincidence. But what's so special about E? Well, E is an irrational number equal to approximately 2.718. It's known as a transcendental number, which means it's an irrational number that's not an algebraic number. It's not the solution to any polynomial. Something that's strange about E is that it isn't geometrically defined, like other famous constants. For example, Archimedes' constant, better known as pi, is defined as the ratio of a circle's circumference to its diameter. The Pythagorean constant, known as the square root of 2, is the hypotenuse of the isosceles right triangle with legs length 1. But E doesn't have any geometric definition like that. E instead has to do with rates of change.
To start with the simplest case, let's look at something with which every adult deals: interest. Now, interest can be compounded annually, semi-annually, monthly, weekly, even daily. Now, all of the formulas that I'm about to put on the screen are going to be of the form A equals P times 1 plus R over N raised to N times T. Now, A is the final amount that we're going to have, P is the principal amount, or the amount that which we start, and R is the rate of the interest, T is the amount of time, and N is the number of times per year that our interest will be compounded. So if we're compounding our interest, if we're applying our interest annually, well, we're just applying it once per year, so N is 1. So our formula will just be A equals P times 1 plus R to the T. Now if we're doing this semi-annually, we're compounding it twice, so N is going to be 2. So our formula will be A equals P times 1 plus R over 2 raised to the 2T. If we're doing it monthly, well, there are 12 months in a year, so N equals 12. So it would be A equals P times 1 plus R over 12 raised to the 12T. For weekly, well, there are 52 weeks in a year, so N equals 52. And you can even do this for daily. N would just be 365. But what if we wanted to constantly compound our interest all the time? So do it continuously. Well, if you notice, as we've been compounding our interest more and more frequently, N has gotten bigger. So if you want to find out what our interest would look like if it were compounded continuously, we need to look at what would happen if N were to increase without bound. So let's do that. Let's just pretend that, for sake of simplicity, that our rate is 100%. So if R is 100% as a decimal, that would just be 1.00 or 1. So what we're going to do is we're going to take the limit as N increases without bound of 1 plus 1 over N raised to the N. Now the limit is just basically asking what happens to this expression as N will approach a certain value. In this case, what happens as N approaches infinity? Well, once we calculate it, it comes around to the value 2.71828182845, etc. And as you may have guessed, this is the value E. This is actually why the formula for continuously compounded interest is A equals P times e to the RT. That's why there's an E in there. But why does this occur? Well, we have to look more closely at how E is defined with calculus. Now, for some basic terminology, the derivative of a function is the rate at which the function changes values. So for example, let's take the function y equals 2x, and let's try to find the derivative of that. What we're going to do is we're going to take the slope. Now, since it's a linear function, the slope is always the same. So the rate of change is always the same. And that rate of change is going to be equal to m, the slope, which we can easily calculate to be 2. Now, this means that the derivative of the function y equals 2x is 2. But that's just a very simple function. Let's go to a bit harder function. Let's do y equals 2 to the x. How do we calculate the derivative of this? Well, once again, we're going to have to take a tangent line. And we're going to have to try to find the slope of that tangent line. So what we're going to do is we're gonna put this line a bit above the tangent line. So we're gonna make it a secant line. And now the secant line intersects at 2 points. Now the difference in the x values between the 2 points, we're gonna notate it as dx. So that's the infinitesimal change in x, which we're gonna call dx. Now we're gonna use the definition of a derivative, which is we're going to take the change in y values over the change in x values. So that's going to be 2 to the x plus dx minus 2 to the x over dx. And we're going to take the limit as dx approaches 0. When dx approaches 0, the change in x is going to continuously get smaller and smaller until it's 0, and then we have a tangent line. So that's why we're taking the limit as dx approaches 0. Now what we can do to this expression is we can separate 2 to the x plus dx into 2 to the x times 2 to the dx because of exponent rules. Now we can factor out a 2 to the x from the limit, and since it's a constant, we can move it outside the limit. So it's going to be 2 to the x times the limit as dx approaches 0 of the expression 2 to the dx minus 1 over dx. Now, the way we can easily solve this, just to get a good approximation, is we can choose very, very, very small values for dx, and we can see what the value approaches. So the limit approaches approximately 2 to the x times the constant 0.6931, etc. Now, what does this constant have to do with 2 to the x? Well, it's actually equal to the natural log of 2. So the derivative of y equals 2 to the x is the natural log of 2 times 2 to the x. Okay, now there are a few important things that we can find out. First is that the derivative is proportional to the function. It's proportional by a factor of the natural log of 2. And this actually works for exponential functions in general. So if we had y equals 2.5 to the x, the derivative would be the natural log of 2.5 times 2.5 to the x. If we had y equals 10 to the x, it would be the derivative would be the natural log of 10 times 10 to the x. So, what is the derivative of e to the x? Well, if we apply our rule, the derivative would just be the natural log of e times e to the x. But what's the natural log of e? That's just like asking, to what number could I raise e to get e? Well, that's 1. The natural log of e is just 1. So, the derivative of e to the x is just e to the x. And this isn't just a coincidence. This is the definition of e. E is the number n for which this expression that we saw in the previous slide is 1. This is how e is defined. So now that means the derivative of e to the x is itself, which also means the antiderivative, or the function that which differentiated is e to the x, is also e to the x. And this actually births a beautiful property. So this is the graph of y equals e to the x. Now, if we take any y value on this function, let's say we pick here, the y value, or the height, is going to be e to the x, right? That point, any point on the graph, is going to have the coordinates x, comma, e to the x. So the height is always e to the x. Now we know that the derivative is also e to the x, and we can equate the derivative to the slope of the tangent line, or the gradient. So the gradient at any point along this function is also e to the x. Lastly, we can equate the antiderivative, or the integral, to the area under the curve. And since we know that's also e to the x, we can say that the area under the curve of e to the x is also e to the x. So e to the x is actually the only function in which the height, the gradient, and the area under the curve are all the same, which is pretty amazing.
E is practically a keystone in calculus, but perhaps the most beautiful fact concerning E is Euler's identity, the equation e to the I pi plus 1 equals 0. It is an equation that brings together all the major constants in mathematics and is often considered the most beautiful equation in mathematics, and it is something I will prove in a future video. At any rate, it is clear that E has much more value than simply being the most used letter of the alphabet.